Steinhauer here, welcome back. Continuing our discussion of star formation and how stars form in the interstellar medium. And we'll start this class with some images of star forming regions. And they are spectacular. In fact, if you look at astronomy pictures of the day, they are some of the most impressive regions of the galaxy are regions where stars are being formed. Why? Because the gas is glowing and it makes for very cool images. This is an example of such a region. This is called the Eagle Nebula. And it's got lots of classic features of star forming regions. One of those classic features is just lots of glowing gas. Again, this is fairly advanced in the star formation process. The star formation process is you start off with a very dark, dense molecular cloud, and then you form a bunch of stars. Those stars turn on, become really bright, and then those bright stars and the winds from those bright stars heat up the gas and blow it out into space, blow it out into the rest of the interstellar medium. And that process is happening as we speak for this particular cluster. And you can see some very bright, very hot young stars right here in the interstellar medium. And these stars are creating a bubble. They are, the winds from these hot stars, very massive stars, are creating a bubble of gas, and you see that as this region right here. There is still some there's still some dark, dense molecular gas stuff like this and this and this, but it is again at the edges of a bubble as the expanding shell from the winds from these very hot massive stars is expanding outwards. And this is if you zoom in actually on this particular region, you get one of the most spectacular Hubble Space Telescope images ever made. This image. It's the same region, and this is called the Pillars of Creation. And you can see, again, you've got in the if you go straight up in this diagram, you've got these hot, massive stars, and the winds from these massive stars are blowing out into space. And the regions of the interstellar medium that were the densest, that were the most clumped, are the last ones to get blown out, if you like. And each of these creates a shadow, right? So if you happen to have a very dense clump of molecular gas right here, it's going to take a while for that dense gas to be blown away by the stellar wind. And so it actually creates a shadow. These fingers are shadows cast by this dense region at the tip of these fingers that's been shielding the regions below from the winds that are coming from those hot, dense stars. You can almost see it. If you zoom way in on this region way up here, you can see the densest of those pockets that are still holding out. There may still be small stars even forming in these regions today. These are the densest and darkest molecular regions of the gas that have yet to be blown away, or in the process of being blown apart by the hot dense gas. So anytime you see an image like this, you can tell exactly where the hot dense gas is, because all of these fingers always point directly back to them, because that's exactly what these are, shadows cast by the dense regions that haven't been quite hollowed out by the winds of the hot stars. One of my favorites. So here's some images of the Orion Nebula. The Orion Nebula is the largest, closest star forming region to the Earth, and so it's the best place where we can study this process happening. And so I encourage you. I'll post a link to this fly through. It's a very cool 3D fly through of some of the interesting parts of the Orion Nebula. But look at some of these stars. You can sort of see it here. Some of these regions of this gas are very non-circular, and there's some very interesting things going on here. And if you zoom in on them, you get regions that look like this. So let's take a look at some of these, right? What is this that we're looking at? What is this that we're looking at? We're seeing baby stars that have just formed, silhouetted against an emission nebula background, right? And so you see the bright object in the middle is the newborn star. What is that dark disk around it? That is the stuff that couldn't quite collapse into the star itself. So angular momentum prevents all of that material from just falling inward onto the star. Some of it will settle onto a disk of material that orbits the central star. And from that disk of material should form eventually, in the next few million years, planets. And so you're seeing in profile, silhouetted against a bright background, the protoplanetary disks of very young stars, disks of material out of which planets will probably form in the not too distant future. You can also see that in an image like this, although this protoplanetary disk, you're not even really seeing the central object, you're just seeing the disk, but you're seeing something else really interesting here. Whenever you have a spinning object and a disk of material around it, it's often the case that as material accretes, meaning transfers from the disk onto the star, some of that material gets wound up in very strong magnetic fields. And when that happens, it can get shot in a jet that goes in both directions out from the central star, perpendicular to the direction of the disk. So, and that's exactly what you're seeing here, a jet of material moving in both directions. Now, interestingly, one side of this jet has a really big hot spot and the other side does not. And it gives this characteristic teardrop shape. And this is called a propylid. And it's caused because the wind in this particular case is moving from top to bottom. The winds from the very hot, stellar, hot, high mass stars is moving in this direction. And so where that wind intersects with the jets, they're moving in opposite directions, they collide and you get a little shock wave that enters there. And you get this characteristic teardrop shape, whereas in this direction, that wind can keep going and going and going, and it just merges in with the rest of the wind eventually. You can sort of see that same shape here. Again, this teardrop shape in this direction is the very hot mass of stars, the wind's coming in this direction, and must be a jet of material that's interacting to cause this spot to be a little bit brighter and to cause this characteristic teardrop shape. Propylids in the Orion Nebula, very cool stuff. You want to see some more pretty pictures of star forming regions? Of course you want to see some more pretty pictures of star forming regions. Here you go. And you can see the pattern remains about the same. You usually get the heaviest, most massive stars, the brightest and the most luminous, coalescing down into the center of that newly formed cluster of stars. And you see the bubble, the expanding bubble of stellar winds, carving out the interstellar medium as it goes and creating these nice circular patterns with small fingers that inevitably always point back to the source of the wind that's carving them out. Here's another one where we've carved out everything behind and in front of and above this cluster, but there's still some dense molecular clouds below it that's hanging on. But again, this newly formed cluster is emitting so much wind that it's blowing away this material, except for this finger of material that's got a shadow and is pointing back towards those hot, dense stars. Okay, we'll end our discussion of star formation by talking about how these stars evolve physically, how their temperature and the surface changes, how their luminosity changes, and why. We call this the life track. We want to track the evolution of stars, and we're going to use the HR diagram to do that. So again, we're not talking about the motions of stars physically through space. We're talking about the evolution of stars on this diagram, how their surface temperatures change and how their luminosities change over time from the time they're born until the time that they reach the main sequence. So let's start at the beginning. Assembly of a protostar. What is a protostar? A protostar is sort of defined to be a star that is still embedded in its molecular cloud, a star that has not yet emerged from the birthing cloud from which it is formed. These stars are typically still accreting lots of material still falling onto them, and they're not even really visible all that much anymore. and we call these things protostars. As a protostar forms, it obviously starts out as a huge, very cold cloud of gas and very dim cloud of gas right down here. It's not even on the traditional HR diagram, which is over here. It's way off the traditional diagram. But as that cloud of gas contracts and collapses into a form, into a protostar, it gets gradually hotter and gradually brighter over time, and it moves up this protostar track until it gets all the way over here onto the HR diagram itself, and then it's sort of visible. It's still going to be contracting, but it's now going to be hot enough that it's probably blown away its stellar the molecular cloud from which it formed. And so it arrives on the HR diagram, interestingly, well above and to the right, the position where it's eventually going to land on the main sequence. So even before, again, this isn't a star. What do we define main sequence stars to be? Those are the stars that are burning hydrogen and helium in their cores. This star has not yet reached the main sequence. It is not yet burning hydrogen in the core. So what is the mechanism that is powering this star at this point? Because it's emitting a lot of light, right? The star, this is an example of a track for the sun. The sun is here on the diagram. At this point in its evolution, though, the sun was more luminous, more than 10 times more luminous than it will be when it reaches the main sequence. What is powering it? How is it getting all that energy? It turns out that the energy generation mechanism at this point is the one that we talked about could have been powering the sun, which is gravitational contraction. The sun has so much gravitational potential energy, and it's so much bigger than it will be as a main sequence star, that it's gradually shrinking over time. And as it gradually shrinks, it converts that potential energy into two things. One of them is it goes into heating up the core of the sun so that it will eventually become hot enough that it can fuse hydrogen, and the rest of it is radiated away into space. And that's why it's so luminous. It's actually very slowly, although generating lots of energy, doing it, shrinking over time and turning that gravitational potential energy into thermal energy and radiated energy. Now, the details of how it gets from 2 and 3 and 4, I'm not really going to go into. It's not terribly important. The important thing is the star will continue to contract, and that gravitational potential energy will be converted more and more into thermal energy. The density and the pressures and the temperatures at the center of the sun will go up and up and up and up until it's hot enough that the fusion reactions can take place in a consistent and equilibrium way. And so that is the details of how it gets from 2 to 3 to 4 to reaching on the main sequence finally. This gravitational contraction is slowly halted, and as it slowly halts, the luminosity goes down until the central core fusion can provide enough energy that the star will remain stable there for its main sequence lifetime, 10 billion years or so. How an object specifically, how a protostar specifically travels across the HR diagram during this time is a rather strong function of its mass. So for instance, here is examples of those life tracks. And again, this is each of these lines represents a path taken by a certain mass star as it travels from the protostar phase to the main sequence phase. It's the pre-main sequence life tracks of each of these stars. And you can see they all start off over here on the right-hand side of the diagram. Although the more massive the star is, the more luminous it is to start. And the more massive it is, the more straight to the left it goes on this diagram before it reaches the main sequence. When you get to the sun, it actually goes quite a bit up and down before it turns around and reaches the main sequence. And these low mass stars are mostly up and down actually before they reach the main sequence. So that's the difference in the pre-main sequence tracks of high mass stars and low mass stars. High mass stars are generally moving left and right on the HR diagram. Low mass stars are generally moving up and down in the pre-main, mostly down in the pre-main sequence to reach the main sequence. Notice also the vast differences in the time scales for these. It's not just that these 15 solar mass stars up here lead shorter lives on the main sequence. Everything they do is faster, including reaching the main sequence, right? Here is a star for a 15 solar mass star that only takes about 60,000 years to go all the way across and reach the main sequence and start hydrogen burning in the core. 9 solar mass stars are way longer than that, 150,000 years. 3 million years for these 3 solar mass stars. The sun, we think, took 50 million years just to reach the main sequence and get hot enough that it could fuse hydrogen into helium. Think about that, 50 million years. I mean, obviously that's a long time, but not on the sun's lifetime scale. The sun is already 4.5 billion years old, but it is a long time on this 15 solar mass star's lifetime, right? Think about a 15 solar mass star. The lifetime, main sequence lifetime of a 15 solar mass star is only about 10 million years. These stars up on the top of the main sequence will evolve to the main sequence, burn all their hydrogen, and evolve off the main sequence and die before a star like the sun even reaches the main sequence. So every stage of stellar evolution for these high mass stars happens way faster than lower mass stars down here. Okay, I like this diagram too. I stole this from the internet somewhere because it shows an interesting and important thing. And in fact, it shows pre-main sequence tracks again of 15 solar mass stars. It shows some giants over here. It shows a pre-main sequence track again, although not in very good detail, a cartoon version of the sun. What's pointed out here though, and this is important, is the bottom of the main sequence. It turns out that there is a fundamental limit to how low mass a star can get and still be a star. So what is that limit, and where do we set it? It turns out the limit is about a little less than 1/10 of a solar mass. 0.08 solar masses is about the lower limit on what you can have and still call it a star. What is the definition of a star? The definition of a star is an object that will reach a main sequence and burn hydrogen in equilibrium in the core. Below 0.08 solar masses, those objects never get hot enough or dense enough or high enough pressure in the core to be able to sustain nuclear fusion at a high enough rate to support itself. And objects that are lower mass than this never reach a stable main sequence burning phase. In fact, they will just continue. You can see we call them brown dwarfs. So below the 0.08 solar mass limit, those things aren't stars anymore, because stars are things that are burning, that have nuclear fusion going on in their cores. We call them brown dwarfs. And brown dwarfs never reach a stable luminosity. They just keep getting cooler and cooler and cooler over time because they don't have a source of energy that keeps them from at a constant luminosity. So there really is a bottom to the main sequence. A 0.08 solar mass star will appear right there. A 0.07 solar mass star will just continue to get fainter and fainter and fainter and fall off the bottom over time. It will never reach a stable main sequence burning phase. So that's what brown dwarfs are. Objects that are below the 0.08 solar mass limit. So here are the evolutionary tracks actually of a 0.01 solar mass object, brown dwarf. And here is Jupiter. Jupiter is a 1/1000th of a solar mass object, and it follows a similar track, right? Jupiter is by far too low mass to be able to burn hydrogen in its core, but it will still follow a path where it gets dimmer and dimmer and dimmer over time as it gradually contracts and uses up that gravitational potential energy. Here is, interestingly, brown dwarfs are some interesting objects because the sizes of them don't vary a lot. So again, as you move from high mass to low mass stars on the main sequence, you're going from physically larger objects down to smaller and smaller and smaller objects. Gliese 229a is an M1 star, right? This is the beginning of the M spectral class. M8 is about the lower limit of the actual stars in the galaxy, right? This is about a 0.08 solar mass object. If you go towards cooler and cooler objects and lower mass objects, you physically actually don't change in size, excuse me, you don't physically change in size all that much, right? So in going from TD1 to Gliese 229b to WISE 1828 to Jupiter, again, you're talking about a range of probably of 100 in mass of these objects, and yet their sizes aren't all that much different. It tells you that an object like TD1 is way more dense than an object like Jupiter. The densities of the objects vary a lot, as does the mass, even though the sizes of these objects, for reasons of interesting thermal physics, don't change all that much as you go down. Okay, this is an interesting demographics of stars. It is not true, and you sort of saw this hopefully if you watched the video of the star formation below. Not all stars are created in equal amounts. In fact, way more low mass stars are created than high mass stars. In fact, for every one star that's made above 10 solar masses, 10 are made between 2 and 10 solar masses, and 50 are made between 1/2 and 2 solar masses. These guys up here that are the superstars, the really high mass stars, are very rare. Not only because they're made very rarely, but because they burn out really fast once they are made. So the vast majority of stars in the galaxy are actually these guys down here, these 0.08 to 1/2 solar mass stars. Most of the stars in the universe are in this mass range. Although most of the light comes from these guys up here because they are by far the most luminous stars in the galaxy. Okay, white brown dwarfs are interesting. There's some satellites that have been launched that have looked for these things and have found them in quite large abundances. In fact, when I was taking my intro astronomy class in the 90s, these had never been discovered yet, but we now know of lots of them. I'll post a link. There's a cool video about the WISE spectrograph that I'll post, and you can see how we're discovering them and learning about them below. So that's where we'll stop today. We'll come back next time and talk about how stars evolve after they leave the main sequence. See you then.